Hi. So I'm just going to launch right in here. I've probably got more than an hour's worth of stuff, so I'm going to go as quickly as I can and hopefully get through it all. Okay. So what we're going to look at through the presentation is the high-level architecture, the high availability model that we're using for 2.0, the Kafka adapter messaging model, and that's important now for 2.0 because we've put a Kafka bus between the adapters and the actual core of VOLTHA. The per microservice architecture for each of the microservices that make up VOLTHA, call flows through the system, and how we're integrating into Kubernetes. There we go. Okay, so I'm gonna point out the areas where we've made changes because that's important. I'm not going to go through stuff that's been in VOLTHA since 1.3. I'm going to assume that there's a background here and people understand it. So some of the important changes that we've made are we've added an affinity routing reverse proxy. So the affinity routing reverse proxy actually takes care of making sure that load is properly distributed and the system understands where to send requests. It also handles active-active capabilities, which means that even if you lose one of the device handlers, or two, the system keeps operating normally. Okay? Another important piece is that we've separated the adapters from what used to be known as the VOLTHA core. The adapters used to be written inside the core as Python code. They've been broken out as their own Docker containers or pods under Kubernetes. And communication between the adapters and the core components is now through Kafka. Finally, the third major change that we've made is that the core components have been split now into a read-write component, the device handler, and a read-only component. The device handlers and the read-only components are all written in Go. So there's no more Python in the core components. In fact, the Affinity Router is also written in Go. There's one final piece I haven't mentioned, which is the AF Router D. So the Affinity Router itself is completely VOLTHA independent. It can be used anywhere where you're using gRPC. It's got a config file. We configure it specifically for use in VOLTHA. And AF Router D is responsible for driving that configuration and interfacing with Kubernetes to push certain elements of the configuration to the router, including understanding when device handlers go away and load balancing. So I'll get into that a little later. So the next thing we're going to look at is the high availability model. So VOLTHA's high availability model is based on two fundamental concepts, redundancy and distribution. Okay, so redundancy meaning that every single operation is always sent to two instances of the core. And the distribution is across a multitude of servers. So each one of those two core device handlers is redundant, and the guy up above is a virtual device handler. Okay, and and what happens is that each one, and we'll see this in a minute, each one of these guys will actually distribute the call across them. And in addition to the redundancy, the virtual devices are the ones that receive affinity or are bound to specific devices, not the lower level guys. So the core pairs, these guys here. These guys are affinity bound to the device that they're managing. And again, we'll see that a little later. So what happens is that when a server disappears or a device handler disappears, you'll find that there's still enough material available to continue to handle requests. So what happens is that those two guys go into high-risk mode, which means that they no longer have an active partner, and the core pair at the bottom is still active-active. And when the server or the core comes back, if a core is lost or a server comes back, the system will resume operating in a low-risk configuration. In other words, everybody will have an active-active pair. And if you notice that the pairs are always on different servers. Now, that doesn't mean that you have to run this on 3 servers. The recommended configuration is 2n+1. It doesn't mean you have to run it on a 2n+1 configuration. You can run this on 2 servers or even on 1 server. It just increases the amount of risk that you're taking on. Because if you lose anything, the whole system goes down. Okay? So I'm going to talk about this very quickly, and the reason I'm bringing this up now is because I refer to it later, and without this quick introduction, you may not understand what I'm going to try and talk about. So the Affinity Router is built per this diagram. So you have servers, routers, backend clusters, backends, and connections. Okay? So requests come in through the servers, they work their way through the system, and then they go out to those core pairs that I showed earlier through the backend clusters and the backend connections. That's all you need to know for now. So I'll go on to the next chart. So here's a conceptual diagram of how all this stuff fits together. So you have the backend cluster. Inside the backend cluster, you have backends, and the backend streams are related to the backend. And so the core pairs, which are the virtual device handlers, are in the backend. So the round robin through these guys occurs at the backend. And round robin is used to distribute the load across a multitude of servers, okay, or a multitude of backend cores. The affinity binding also happens at the backend level. So the round robin happens at the cluster level. The affinity binding happens at the backend level. So a backend consists of this virtual core pair, which translates to 2 streams to converse with 2 separate Kubernetes pods or device handlers. So there's 2 modes of binding that occur in here. One is southbound binding, which means that when a southbound request hits the Affinity Router, it will decide it will check to see if the device has already been bound to a virtual core pair. If it hasn't been bound, 2 things can happen. One is, for certain methods, it'll get bound southbound, which means that the device ID is known. The binding will occur southbound by doing a round-robin jump to the next available core. The binding will take place there, and every other call after that will use that binding to communicate with that core pair. Okay? There's also a northbound binding, and that happens with a single method, which is the create device, or also known as pre-provision, because the device ID isn't known southbound. The device ID is only known on the response to that request. And so the binding will occur northbound. So how is this selection handled? So the selection is handled by using different aspects of the remote procedure call, or the RPC. There's 3 elements that participate in the decision making. There's the package, the service, and then a field in the protobuf. In VOLTHA's case, it's the device ID. Okay? In other cases, it can be anything. It's a config parameter for the Affinity Router. So what ends up happening, so now this this hopefully will gel everything together. So when a request comes in through the northbound end, let's say you made a request to change something on a device. The request is going to hit the front end of the Affinity Router. It's going to look up the affinity in the table. If it has it, it's going to go to the corresponding back end, and it's going to send the request southbound. And that's going to go hit both core pairs. So it's going to hit both of those core back-end streams, and then that will hit both VOLTHA core components, or device handler components. And those device handler components are actually going to race to get a key, and that in etcd. And that key is a serial number that was assigned by the Affinity Router as it sent the request down. It's in the header. So they will take that serial number, and they're going to try and lock it in etcd. And whoever wins the race actually gets to service the request. So what happened here is the guy on the right won the race. The guy on the left gets locked out. So he just trashes. Well, he doesn't trash the request right away. He holds on to it for a little while. And the core or the device handler that won the race will actually send the response back northbound, and then the request store will get the response. Now, should the guy on the right actually never complete the transaction, the guy on the left will actually take it over. And what happens here is he will send a response back through the back-end stream. And what happens is that within the affinity routing mechanism, the first guy to reply actually wins. So if something goes wrong, and this core here takes over from the one that did not respond in time, the response will get locked out on the other side at the router. So even if the other guy does respond a little later, let's say he's been slow, he's been bogged down by something, even if he sends a response back, it gets ignored and trashed. And typically the response that he would send back, since he never completed his transaction, would be that the transaction failed. But the other guy sends a success return, so everything works out fine. So that's the redundancy and the high availability model. Any quick questions on this? Or was it clear as mud? Yes?
So when they race to find get the log,
yeah.
And one of them wins
yeah.
and responds, what if that response never comes? How does the other one know that the response never came from the one that won the log?
OK, so what the other one does is it waits for a timeout. And if that timeout occurs before the key is released in etcd, it assumes that the other guy never actually, or the key disappears in etcd. He assumes that the other guy actually never completed his transaction and tries to reply. Now, if the other guy did reply, the Affinity Router will block him anyway, okay? Because there's also that mediation that happens at the Affinity Router itself. It's based on a timeout today, okay? But there is the mitigation further north that only one of the responses is allowed to go back. And it's always the first guy that wins. Any other questions on this? Yes, it's a gRPC reverse proxy that does a few more things. And there's an architecture diagram for that, which I better speed up or I'll never get to it. So the Kafka messaging model. So very quickly here, the Kafka messaging model is used to communicate between the cores, or the, I keep calling them core, and I know that we don't want to call them core anymore. We want to call them device handlers. So the device handlers use the Kafka bus for communicating with the adapters. And I put one broadcast topic there, but there's multiple broadcast topics there. There's a broadcast topic for all the device handlers. There's a broadcast topic for every, for multiple instances of the same class of adapter, okay? And then there's topics per device. So what happens is that every time a new device appears, a new topic gets created, and the communication happens through there. Should, let's say, a message come up through one of these adapters that doesn't have a device topic created, it will post it on the broadcast topic, and it'll get picked up by one of the device handlers and handled that way. So the device handler will then create the topic, and then the two will communicate through the topic from that moment forward. So, for example, the discovery of an ONU, the ONU doesn't exist initially, and when it's discovered, then the topic will get created for it, and the communication for that will happen through the created topic. So that's the Kafka messaging model. And today we're using Kafka. It could be some other message bus in the future if Kafka starts having performance issues. We're going to be testing this at scale. So if we start seeing that there are performance issues, there are other message buses that could be used that have much higher performance and still use the concept of topics. So now I'm going to get into the per service or per microservice architecture. So this one, this depending on how many questions are, actually, were there any questions on the Kafka? Yes.
From adapters to the device
Handler.
is there any kind of communication mechanism?
It's through, yeah, it's gRPC. So yeah, it's basically a gRPC payload thrown on the Kafka bus and picked up by the other end. Yeah. So we're using well, not gRPC, it's a protobuf. Okay, it's a protobuf that goes back and forth. Yes.
I'm not familiar with the mechanism of Kafka, but I'm afraid of message drop in the Kafka.
So Kafka's reliable. Okay, it's supposed. So the whole reason behind Kafka is that it's got high reliability and it keeps every single message in the queue until you reset your index or your offset. Okay. Yes, it's designed to be, and it's redundant. There's 3 instances or 5 instances of the Kafka process running. Okay, so and that's why we chose it initially. But there are other message buses that are written in Go, as opposed to the Kafka bus is mostly written in Java. There are Go implementations of message buses that are a lot more performant. The only thing that worries us a little bit is that they don't guarantee ordering. Which
I do suggest the audience here, if something you have to answer right away, and you ask a question, otherwise.
Okay, you're worried about me not getting to the end of this, aren't you? Okay, so let's look at the Affinity Router. I'm gonna try and do this quickly, but there's some important stuff in here. This is a new piece, so I'm gonna go into this one in a little more detail. Anything that's new, I'm gonna do more detail on. Anything that's old, I'm not gonna do a lot of detail on. Okay, So first of all, the Affinity Router is made up, as I said earlier, of servers, backend clusters, backends, connections, and streams. Okay, that is basically the structure of the Affinity Router. And so if you trace a request through here, it comes in through the north. Okay, and based on the package and the service of the proto itself, it decides what router and backend it's going to use. Okay, so the server uses that to determine the router, which determines the backend. So the server handler does that determination, hits the backend cluster, and the backend cluster handler takes over. What happens in the southbound direction is at this point, the backend cluster needs to understand which backend to use, whether Affinity has been established or whether it hasn't. Okay, that's important. So at this point, what it does is it actually goes back to gRPC and does a get message. And when it does that get message, it basically gets the entire protobuf from a gRPC. But what gRPC does when you do that get message is it actually goes to a codec and tries to do an unmarshal on the message, which, of course, the router's not going to do because it doesn't need to understand the entire message. But it does know enough based on the proto descriptor file, which it's loaded early on from here, how to extract the ID from there. It throws it in the frame, and then the backend cluster, after it's gotten the message, the actual frame that contains the gRPC message also contains metadata that we've added in there. And in that metadata is the actual router and backend. So the codec's gone to the router. It's figured out what backend to use. That gets back to the backend cluster, so it knows what backend to call. One of 2 things happens when the router is called. One, either there's an affinity that's been established, so it tells it this is the back end that you've got affinity to, so that's where your device is, or it hasn't been established, it does a round robin on it, picks the next available back end, and then establishes affinity with that back end and returns that back end. Okay, so one of those 2 things happen. So then the back end goes to the back end handlers. The back end handlers basically ask set up the connection. And when they set up the connection, they go through the stream handlers. And what happens at this point is that if you look at the blue arrow that goes from the gRPC server through the stream handlers down to the clients, that's where the whole communication gets bound. After all that happens, it's just straight pass-through back and forth. So if it's a streaming gRPC call, then all the messages just go through there, and that whole mechanism that did the association initially is left out of the picture. If it's a single non-streaming gRPC call, it just operates till EOF, and then it drops the stream. Okay? Any questions on this?
Don't ask.
Hey, I mean, it's okay. We can get a question or two. Okay. So if this is okay and it's well understood, then I'll go on to the next one. So the affinity routing daemon microservice. So as I said earlier, the affinity router is pretty much independent of VOLTHA. It can be used for any gRPC implementation with any kind of protobufs. It doesn't matter. It's all held in a config file that's extremely detailed, that tells the router what it needs to do. And so what happens is that the affinity router daemon actually is the one that writes part of that configuration. So there's a configuration template that's loaded by the router, minus all the back-end information. And so what the daemon does is it calls a Kubernetes API client to find all the VOLTHA device handlers running. And the reason it needs to do that, it can't use DNS because it really needs to understand what piece of hardware each one of these guys is running on to establish redundancy. Okay, so the backends are redundant, right? There's one on one server, one on a different server. The only way to know that is to actually call the Kubernetes API. DNS won't do that for you. So basically, it calls the API, and then it uses a backend allocator, and that backend allocator basically uses an intersection. An intersection between backends. So let's say this thing's crashed and come back up. You know, all these device handlers already have affinities established, right? They have devices that they're managing. So this actually calls the backend the gRPC API of each one of these handlers to determine what devices they're handling, so that it can do an intersection, figure out who had what, and make sure that everybody's distributed across the hardware correctly. And then it calls the Affinity Router config client, and that pushes a new configuration down to the Affinity Router, which tells it for each back-end connection what the IP address and port is that it needs to be talking to. So that sets up your completely redundant back-end and your virtual device handlers that have two redundant backends or two replicated backends. So this is also a new component that's been added.
So this is established before any hardware device. I mean, OOT.
Well, it does it. So when it starts up, before anything's been established, it uses it tries to do intersections. There's no intersections, so it just allocates the backends based on hardware. Okay, so to make sure that there's always pairings across hardware. If something crashes, if the Affinity Router itself crashes and comes back up, then all these guys actually have devices that they've already started managing. So it'll query them to establish the affinity, so it knows, so it can reestablish its knowledge of affinity. Because once you've crashed, you've lost your in-memory image. This is not storing anything in a KV store. So it just re-queries all the device handlers. First, it needs to figure out an intersection to figure out who was paired with who, right? And in order to figure that out, you need to do the intersection between two device handlers to find a non-null set, right? And then it can reform the pairings it had before the crash. And so all that's been built in. And it's done by this guy. Okay, any other questions? No? Okay. No, we're doing well. Yeah, we're doing. I think I'll get through all this stuff. Thanks to your help on not getting too many questions. Okay, so the device handler microservice. So this is a lot of this stuff is all old stuff. What's new down here is these pieces here for Kafka communication southbound, the transaction handler. And that's about it. The device manager, logical device manager, it's all been rewritten in Go, but it's the same thing that you would find in VOLTHA 1.3. So the transaction handler is the one that uses the serial number to disambiguate which of the two backends is going to handle the request. Okay, and the Kafka messaging proxy, and we actually put in this proxy here because we may want to replace it. We may want to replace Kafka with something else, so it acts as a shim to keep us independent of the actual message bus that's being used. Okay, and we've done the same thing here. We've got a KV shim, and the whole reason we have a KV shim is because maybe we want to replace etcd with something else. Okay, so what we've tried to do here is we've tried to decouple the internals, so the data model. We've tried to decouple the data model from whatever we're using here. Today it's a KV store. Tomorrow it may be a NoSQL database or something else, right? It could be Cassandra for all we know. Anyway, so those are the new components that we've got here. Any questions on this?
Is database is shared between all the cores?
Yes, it's the same database for everybody. There's one etcd database, but it's etcd is distributed, so there's multiple instances of it running for redundancy.
Just a quick question about the data model. What do you mean the data model? Is that the device, the XGS model, model, or what data are we talking about?
So we're talking about the device data. Okay. So the device data, flows, provisioning, all that stuff is in there. Okay. The read-only microservice is dead simple. Okay, so the read-only microservice doesn't even have a southbound. It goes straight to etcd, pulls the data, and returns it. Okay, so there's no need for it to communicate anywhere southbound. The read-only microservice is a straight round robin. So requests are made to each one of the 3 or 5 or 7 read-only microservices running across the servers. And again, we've got the, even though I put the data model straight into the KV client, the shim is there as well. By the way, here, I probably drew this too fast. Okay, the adapter shims. So what we've done to simplify things is we've actually written a shim for the adapters. So anybody implementing the OLT adapters and the ONU adapters really need to implement this section here. All the rest of the stuff up north, we've actually taken care of. So there's two different, and we'll see that a little later, but there's 2 different channels that these things are taking through Kafka. One is communicating with the device handlers, but the other one is an inter-adapter request, so OLT to ONU adapter request. Actually, it's more ONU to OLT, because the OLT is the one that sends all the OMCI commands down to hit the ONU. So that communication also goes through Kafka. So these guys, and one thing we've been toying with, and we haven't settled on that yet, is that maybe rather than sending this stuff back and forth across Kafka, we use Kafka as a discovery mechanism and then bind these 2 together with a direct gRPC connection to improve performance. Okay, but we haven't settled on that yet. So right now, this is the way it's implemented. Any questions on this? Yes.
So are these shims are in Go, or they're still specified?
These guys are in Go. Yeah, yeah. Yeah, we anything new that we didn't do in Twisted. We tried to get away from it just because of the ugly nature of that framework and the complete lack of debuggability. Okay, so we got 2 sections left: transaction flows through the system and tie into Kubernetes or interactions with Kubernetes. So we'll get straight to the transaction flows through the system. So I sort of mentioned a lot of this stuff already earlier on in the talk, but I'm going to go over it anyway, just so that. So what happens is that there's 2 ways to get in. Either you make a REST call through Envoy. Envoy converts that to gRPC and gRPC into the stack, or straight gRPC into the stack. Okay, and we'll see later how Envoy is packaged in there. So it hits the Affinity Router, and what happens is that the call goes through, as I said earlier. So it hits the server. The server selects the router based on the package and service. It uses the router to find the backend cluster, and then the backend is found based on the information in in the protobuf itself, one of the fields in the protobuf. And then it goes through and it creates two streams and sends it down to the device handler. I'm only showing one of the device handlers here. So the flow, once it's gone through there, it hits the device handler. The transaction handler takes care of determining whether or not it's the one that's going to actually process the request. And then once one of the two has successfully acquired the lock, it goes through the core, does the request processing, and then goes through the proxy handler, through the Kafka bus, and to the OLT and ONU adapters, and then the OLT adapter is the one that communicates with the actual physical devices. Okay? Any questions on this? This is basically the end-to-end view of how everything transpires on a northbound request. So this is a read-write request. A read-only request is much simpler. It goes through, it does a round-robin selection of a backend and executes the read, and that's it. Okay. The actual read-only cores have a cache so that they don't have to keep loading information, but as the stuff ages, it gets tossed out of the cache. This one's a little more interesting. So this does the initialization for control plane packets. Control plane packets, I mean DHCP, IGMP, EAPOL, all the ones that come up through the system. I don't know what that was. Okay. Okay. So it's handled a bit differently. For those of you who have been in VOLTHA for a while, you know that the OpenFlow agent or the OF agent is bound directly to a core one-to-one. And that's because it represents all the devices that are handled by that core, okay, or by that device handler, okay. So in order to respect that binding, the Affinity Router has a binding router. So there's an Affinity Router, there's a round-robin router, there's a binding router. There are other types, but they don't apply to VOLTHA. So what happens is that when a request comes through the system, the binding router will look for the next unused core. Okay, so let's say an OF agent makes a gRPC call to initiate the connection. It will look for the next unbound core. If there are no unbound cores, it'll reply back saying, sorry, you're out of luck. They're all taken, which means that you've already got all of them bound by OF agents. So there's a rogue OF agent trying to connect that you don't really need for anything. So what it then does is it will actually open streams to both of the device handlers, but send control plane packets only through one of them. And the device handlers actually will pick up information coming from the south off the Kafka bus and send it north only through one of the two handlers. And this is a streaming connection, so it will stay open and until something crashes or somebody shuts down nicely and closes the connection. Okay, so this is a streaming gRPC call. Now, what's going to happen though is that the other one is open. The other stream is open, and should anything happen to the connection to the first stream, what the router is going to do is it's going to switch over and say, I'm going to use the alternate stream, and until such time as the other guy comes back and the connection gets reestablished, or not. It'll continue to use the other stream permanently after that happens. So this is a bit of an exception, and we're actually trying to figure out a methodology whereby we can send the control plane packets up both paths the same way we're doing with the gRPC requests, okay, the standard control requests, so that you've got complete redundancy until such time as somebody puts something on the Kafka bus, and when one of these device handlers pulls something off the Kafka bus, it'll split it both ways and send it north again through both handlers, and then the router will take care of, the Affinity Router will take care of tossing one of the two before it sends it northbound to the OF agent. But for the time being, it's an active-passive as opposed to active-active for all those packets. Okay, so for the packet outs and packet ins.
It is transparent to adapter, right? They don't care.
The adapters don't care. In fact, you could implement a redundancy scheme for adapters where you have 3 or 4 adapters and you need to 3 or 4 instances of an adapter to have redundancy, but you have to make sure that only one of them for now is sending the information up through the bus.
It's a packet, you know, the detail. Is this the first implementation of this kind of the redundancy, you know, about the packet in strings, right? So are there other applications right now in the world, you know, who actually have a resolution on this one? Is what I'm saying here.
Yeah, no, I don't think, well, so lag is an example of a redundant communication stream for data, right? So you've got 2 paths and they're both being used, and when one dies, then only one gets used. Now, with lag, everything going across both it's being hashed across both, right? Whereas in this case, there's no hashing. It's the same request going up both channels. And one of them has to be discarded at the last minute before it gets to the top. Right? What this saves you, so the only thing that the redundancy will buy you is if there's a packet in flight and one of the members along its path crashes, the other one will get through, right? If you don't have this type of redundancy and you wait for a crash before you switch to the other stream, what ends up happening is that let's say the IGMP request in flight will get lost. So that means the guy who changed his channel didn't see the channel change and he'll have to hit the button again, okay? Which isn't a big deal, but if you lose an EA poll, then you know there may be, like if timeouts start happening, you know the user, you get a reduced user experience in the end, right? Because something gets lost, they get frustrated because they tried to change a channel and it didn't work. So that's really the only big drawback of not having the redundant communication is the crash during the transmission of the packet.
And potentially the operator can come back to us, you know, we don't really need this, right? So we can afford a little bit delay, that's fine. So,
Yeah.
Yeah.
Yeah, well, but then you're back to this model, which is I'll just switch over to the other one if the first one disappears,
Okay.
right? Because the thing is, you do need the switchover redundancy, because if you lose a server, then you want to switch to the alternate, right? You don't want it to go offline for an hour while somebody's trying to fix it, because then you're going to be losing a lot of IGMP packets and a lot of DHCP and all those others. Any questions on this? Sean wanted no questions, but he's. Okay, so I'm almost done, so I'm going to be ahead of schedule. So hopefully Shad is ready. Okay. So Kubernetes integration. So this is my last section. So I'm going to talk about how we do our Kubernetes integration. So each microservice runs in its own pod. So the device handler microservice runs in a pod. The read-only microservice runs in a pod. Kafka runs in its own pod as well, 3 redundant pods. So does etcd. The only exception is the Affinity Router, which basically runs in the same pod as Envoy and the Affinity Router daemon. Okay, so they're all grouped in one pod. So the Affinity Router daemon and Envoy are sidecars that are used for different purposes, along with the Affinity Router D. So as I said earlier, what ends up happening is that the daemon is responsible for configuring the router based on the environment. So what this means is that if you don't want to use Kubernetes as your container management system, you can use anything. There's just one change to make inside the Affinity Router daemon where it queries the actual pods or containers that have the device handlers, and the whole thing will work with another system. Okay, so it's a very small change, and it shields the router from knowing anything about VOLTHA at all. Okay. So what happens is that in this integration, the actual queries are happening on a regular basis. So the daemon is querying the Kubernetes API regularly to know where all the pods are and what they're doing. So if pods disappear, it'll know about it, and it will actually push a config down immediately to the Affinity Router to say these guys are gone. The Affinity Router should already know because the connections would have been broken, but it pushes null configs down so that it doesn't even consider them anymore, right, as candidates to keep performance up. So that was everything I had, and I'm really early, which is great. So we have time for questions. So does anybody have any questions? Yes?
So you talked about the device handlers are being handled as a core pair or a pair.
Yeah.
Two different servers. Can you talk about the affinity and the instances of the adapters themselves? Is there one per OLT or physical OLT, or are you having a pair of those that are being?
So the question was, I talked about the device handlers being paired into redundant pairs, right? And so the question was, what about the Affinity Router and what about the adapters, okay? So as I said earlier, the adapter developers can choose whatever model they want for high availability or none, depending on how they want to do the implementation. As far as the Affinity Router goes, today it's a single instance, but there's a plan to put a second instance in that will be running, and these guys are just going to keep in sync with a streaming gRPC interface between them. So I can explain how it's going to work. It's going to take me a few minutes. So what's going to happen is that when the Affinity Router processes a request, it's got a running serial number and affinities that it's established while it's operating. So what it's doing is that at the completion of every successful request, it will actually, and this is important because you need to handle split brain. If for some reason these two guys are not viewed as one by the outside world and the same request goes to both, you could actually wreak some havoc. So what happens is that when a transaction completes successfully on the primary Affinity Router, it's a primary and a standby, it will send any new affinity established and the current serial number to its peer. So the peer knows the serial number. What happens here is that should the peer send a request down to one of the device handlers that has a serial number equal to or less than the previous serial number, then the device handler knows to ignore it, because that means that for some reason the backup went and received a request it shouldn't have received because the primary's already processed it. So that's the intent. So the intent is there'll be two of them. They will have a floating IP or a DNS entries so that you can just switch to the other one should the primary go down. Okay, and the switchover will be handled by the secondary when it loses connectivity with its peer.
Is there affinity between read-only microservice and device handler?
No. So the read-only microservice is strict round robin. It just goes around and asks the next guy and the next guy and the next guy for reads. They read the data straight out of the KV store, cache it for a while in case there's another request that happens to hit it. So the actual affinity is not used at all for reads.
Cache is local to read microservice, right?
Exactly, yes.
So then if you do round robin, then what is the use of that cache?
Well, it may come back and request. The aging's pretty quick. So yes, you're right. If I get 3 requests for the same device in a row, the three different guys, but it's for load leveling. The intent behind round robin is mostly for load leveling, and affinity is to make sure that you're actually distributing, and specifically for the device handler, because they keep all the devices that they're managing loaded in memory at all times, right? So you want to distribute that evenly across your cluster. You don't want one device handler having all the devices. So round robin ensures that every time a request comes down that's not already established, it goes to the next guy and then the next guy. And then so the round robin only happens. So there's actually multiple round robins, right? The device handler round robin being handled by the Affinity Router is different from the read-only round robin. They have different indexes, right? So they're going around, one of them's going around all the time, and this guy's only moving forward if the affinity hasn't already been established, okay? So that way you get the one that's holding the most, that's hogging the most memory, which is the device handler, spread evenly across all your servers.
So device handler, does it have any guideline how many devices it will handle?
That all depends on how much memory you have available to the device handler, right? We're actually going to do performance and scalability testing. We've done it before on VOLTHA 1.3. And what we're going to do, I can explain this since I do have some time. So what we're going to do for VOLTHA 1.3 had the concept of a simulated OLT. And a simulated OLT was really, it did nothing but receive the request and create this virtual device inside of it, and then generate alarms and PMs on behalf of that device. And so what you could do is you could create thousands of these guys, and you didn't need, like PonSim is a problem because you need interfaces for PonSim, and if you wanted thousands of PonSims on a server, you wouldn't be able to create them, right? Whereas with the simulated OLT, it has no interfaces. It's just really a virtual OLT and virtual ONUs, right? So what we're going to do is we're actually going to create an adapter that replaces what used to be called the simulated OLT. And then we're going to start making requests, thousands of them. And the way we typically do the scalability and performance testing is we use VMs and very small VMs. So we use a 6 gig or a 12 gig VM, right? So it doesn't have a lot of memory, which means that you hit the memory limit pretty quickly, and then you start seeing what the system behavior starts to look like when you hit your memory limit. So that's what we did in VOLTHA 1.3. We're going to do the same thing here. So we're going to start creating thousands and thousands and thousands of OLTs, and they're going to be generating alarms, and they're going to be generating PMs, and we're going to see exactly when it falls over.
So this simulated OLT will be also container, or?
Yeah, it's going to be a container that's going to connect to Kafka like any other container.
This container will handle thousands of devices?
Yeah, it'll look like it's got that. Well, it pretends it's got thousands of devices, but it's connected to nothing, right? So to be fair, we should really put it on a server outside of the three that are doing and that's easy to do, right? We can create a fourth VM, make sure that Kafka extends out there, and that this guy's sitting outside of the test scope.
Because we have to decide on OLT adapter container, how many devices each container can handle.
And that's up to the designer of the adapter, right? This thing is really not an adapter at all, right? There is no southbound. It's not communicating with anybody. It's self-contained, and they're just little virtual devices that get created inside it in order to create devices inside VOLTHA, right? So VOLTHA can be handling them.
No, you're fine.
It sounds like the adapter authors don't get any benefit from the redundancy model built by the device handler's warfare. We'll have to do the redundancy again. Because all the device handlers are doing is one or the other is going to put out a message on the adapter.
So
Adapters will pick up.
So since none of the adapters have been implemented today, one of the two puts the message out on the Kafka bus. Should the adapter designer say, I want to participate in this redundancy, so please send both requests down, there's no issue. We'll send them both down and let the adapters do the disambiguation of the request using the same mechanism that was being used up north, right? There's nothing stopping that from being sent down both paths. In fact, because it's on Kafka, you don't actually need it to be sent down both paths. All you need to do is pick it up with two adapters and then decide which one of the two gets to handle the request, right? Because it's going to make it to Kafka. Once it makes it to Kafka, you can have as many listeners as you want picking up these things, these messages. So we could either A, put it on two topics, the primary and the redundant topic, which to me is the same as putting it on one topic and letting two adapter implementations or two instances pick it up and then decide who's going to do what with it. So you can have so that allows you a lot of flexibility in your high availability model, right? You can say, I'm going to implement it with two. One's a backup, one's a primary, and the primary's picking stuff up, and if the backup loses communication with the primary, then the backup starts doing the work, right? So, or they're active-active, and they disambiguate using a race to a key, the same way we're doing it with the cores. So, I mean, Kafka really won't lose a message. So how many instances of that message you pick up is up to you.
Is there any persist data within the core system so that when it reboots, you have the data already?
It's in the KV store.
All that data is persisted?
Yeah, all that data is in the KV store. And what? So what happens is, so if you reboot the system, it starts off clean, which means that the cores will no longer have any affinities. Nobody will have any affinity established. It's all going to get reestablished as the system starts to run. But let's say a core crashes. One of the device handlers crashes. What's going to happen is that when it comes back, the Affinity Router daemon actually, this is one part I didn't explain. The Affinity Router daemon is actually going to tell it what devices it was handling before it went down, because it's paired with another instance, right? So when it decides which one of the device handlers that's come back is going to get paired, it's going to say, okay, I'm going to give this guy all the information the other guy has, just IDs, right? Just the device IDs. And he's going to sync the data out from etcd. So we're going to give it IDs, and it's just going to pull all the information from etcd, and then they'll both be having the same information. So they'll be backups of each other again.
So will the Northbound API of VOLTHA change compared to 1.x, or are they pretty?
They're pretty much the same today. There's no big changes northbound, the only big change is, and actually there's not a big change southbound either, because southbound we're using the iAdapter interface, and there have been very few to no changes to the iAdapter interface. It's
only logical interface related things have changed because adapters no longer handle logical.
Yeah, that's right. That's right. So that's the extent of the change. There's not really a lot of big changes that we've made to the interface as we're trying to keep those.
Changes like add port is changed to port created kind of thing.
Yeah, and activate was changed to enable, and there's a few things that but it's not big.
And the interface already published in the VOLTHA discuss, right? So
Yeah.
we do have that in the
Yeah.
VOLTHA wiki. And then we have about 2 minutes. Any other questions? How much harder or easier do you think the system is to debug compared to VOLTHA 1.x?
I think it's about the same. We have logs everywhere. It's fairly easy to understand what's going on. And easy enough to trace a request through the system. So I would say it's about the same, because VOLTHA 1.0 had multiple cores as well. They just weren't redundant, right? The only extra work that you have to do here is figure out who picked up the request of the active-active pair, right? Which one of the two picked it up, and the router will actually tell you which one it sent it to and who gave it a reply. So that can be forced into a log. I mean, we're not going to log that for every request. It's silly. We'll slow the whole thing down to a crawl. But if you're trying to debug an issue, you can turn on the debugging logs to the point where you actually get that trace information.
And last up, Sean also raised the hand.
Yeah, so for the
Speak louder.
for the adapter redundancy, would you be able to use a mirror image of the Affinity Router and the core? Because you have a single physical OLT bound to a pair of adapters, essentially.
Mm-hmm.
Is that kind of like a reverse OLT?
So initially we had discussed putting a reverse proxy at the bottom as well. You can use, if it's gRPC, you can take the Affinity Router and use it almost directly, except it's got to be an inverse. So the server would be pointing down and the client would be pointing north, right? And it can be done. It's just a matter of the configuration file being set up for it. So that can be done. I basically, sorry, I know I'm over time now. I shied away from it because I didn't know what the adapter implementation teams were going to want to do, right? So I said, look, I don't know what they want to do. I don't want to force a paradigm on anybody. So once the adapter developers say, hey, it would really be nice if I could do this, then maybe we can.
I think we will definitely look into the adapter redundancy. I think that's one of the requirements. Okay, thanks, Sergio.
Thank you. And now it's
now it's a
Shad.
Yeah, Shad.